Okay. So CMP is molar heat capacity at constant pressure. Then delta theta is change in temperature. Q is quantity of heat supply. W is work done by gas. Delta U is increase in internal energy. Then we will go to 10.2, we go to work done by gas. That is the formula. Integration. P is the pressure lah. dV is the differential in volume. First law of thermodynamics. Q equals to delta V plus W.
Yeah, so why the 10.3 the formula like that? Huh?
You be patient lah. You have to explain step by step.
Okay.
Suddenly. Q, yeah, if you will work with molar, so that is the formula for molar. Just be patient. And that is your delta.
Okay.
Delta U is N times your C M V delta theta. And then you need to know isothermal and adiabatic changes. Okay. For kinetic theory of gas, we look at ideal gas. We need to remember all this formula. N is the number of mole, and then the ideal gas formula. Right? And both of them you need to know. Then pressure of gas, that is the pressure of gas formula. And molar kinetic energy, kinetic energy per atom, 3/2 kT. Then root main crash speed, degree of freedom, average kinetic energy, and then F is the degree of freedom. Okay, so all these formula must be in your head. So degree of freedom is just the independent mode of acquiring kinetic energy.
Yeah, the translation, rotation, vibration, right?
So it's monoatomic, you got 3 translational, no rotational.
Yeah.
If it's diatomic, you got 3 translational, 2 rotational. Polyatomic, you got 3 translational and 3 rotational. And internal energy, that's a formula, sum of kinetic energy for ideal gas. Okay, so all this you must remember. We'll be using a lot of these ideas. So that is summarized for you. Internal energy is your F divided by 2 NKT or F over 2 nRT. Okay with that? So heat capacity.
Okay.
Right? Remember, heat or thermal energy is a form of energy. Internal energy of a system is the sum of the random distribution of kinetic and potential energy associated with molecule of the system. Right? There's intermolecular force. That's why they got potential.
So internal energy is basically combination of kinetic and potential energy.
Yes. Kinetic because it's vibrating, it's moving. Potential because there is intermolecular force. You think of it like spring, you are stretching it. Can?
Yeah, okay, understood.
So internal energy is determined by the state of a system, and it can be expressed as a sum of kinetic and potential energy, as I've done written for you, summarized for you there. But if it's ideal gas, remember ideal gas is the sum of kinetic energy of the particle. There's no intermolecular force, so there's no potential energy.
That means there's no potential energy.
No potential energy. Can write
Hey,
it.
how come got no potential energy?
No intermolecular force.
Meaning?
Okay? No spring, no intermolecular force.
Oh, okay.
Okay, now, so it's mainly
That means just keep on moving.
It's just moving only.
It's not like expanding or not. It's not right.
Yeah.
Okay.
Right? No intermolecular force, so no potential energy. Okay, so you can summarize. Energy depends on state of system, whether it's solid, liquid, or gas. A rise in temperature is due to an increase in energy. Energy is independent of the pressure and volume of an ideal gas. Right? Remember the formula we have derived early in your previous topic, topic 9, right? Where the energy is proportional to the number of degree of freedom and proportional to temperature. Okay? That formula is important.
1 minute answer.
Okay?
No, the internal energy is basically ideal gas, right?
Yeah, we are looking at ideal gas only.
Okay, so rise in temperature is because of the ideal gas only.
Yeah, you can see from the formula. Temperature rise, internal energy rise.
Okay. Oh, that's why they
Remember?
say it's independent of pressure and volume.
No volume, no pressure there.
Oh, that means it's trying to say no volume, no pressure lah.
Mm.
Okay.
Okay,
Okay, you can continue.
so thermal energy and internal energy. So thermal energy is something it's just energy, Q. So when it enters matter, it becomes internal energy.
That means it becomes the ideal gas lah.
No. If it enters matter can be solid, can be liquid or gas. So
Yeah.
thermal energy is just energy, it's a form. So when it gets into the molecule, it becomes internal energy already. So when the
Yeah,
matter,
that means it become ideal gas energy already lah.
so we are more interested in ideal gas. We are not interested in solid and liquid.
Yeah, no. What I'm trying to say is because like teacher said thermal energy entering, right?
Thermal energy is just the energy that flow because of different temperature.
Yeah.
When it enters the
So when
matter, it becomes internal energy.
okay.
Right? So we know that matter is heated, it expands as its temperature rises. The rise in temperature is shown by the increase in internal energy of the matter. Okay?
Correct.
Remember the formula I've given you earlier? Temperature rise, internal energy rise.
Temperature rise, energy rise.
Okay. Right? If you look at a small swimming pool and a kid paddling pool, you put in the sun, it takes a lot of time to heat up the swimming pool.
I mean the bigger one will take long time.
Right? So it got more heat capacity lah. For the bigger one, smaller heat capacity. So we define heat capacity, capital C, as the amount of heat required to raise the temperature of a given object by 1 Kelvin.
Yeah, so that means heat capacity for the bigger swimming pool means need more, the smaller one need less, right?
So for a change of
opposite.
So for a change of temperature delta theta,
Yeah.
the quantity of heat is just C times your delta theta. Unit of C is just joule per Kelvin or joule per degree Kelvin Celsius. Okay, you can derive it. C is Q divided by delta theta. So unit joule Kelvin. Okay with that?
So the C equals to delta theta over theta.
Q over delta theta.
Oh, sorry, Q over delta theta. Yeah. That's why it's J over K lah. Okay.
Yep.
Got it.
So heat capacity, not a useful quantity because it depends on the material and the mass.
Okay.
That's why a small bucket of water in the sun would heat up faster than a pool of water in the same sun. Both water has different mass and volume. Okay, with that?
1 minute, Acha. Yeah, okay, understood. Teacher, how come the water has different mass and volume? I thought all water has the same
Oh, no,
mass.
no. This is a small bucket. Small bucket got smaller volume and smaller mass.
Oh, okay, okay, okay.
Got bigger volume, bigger mass.
So it's depending on its size and shape.
Mm.
Okay.
Then we define a more useful quantity, specific capacity. Kinetic energy for a substance shows a rise in temperature. Increase in kinetic of a substance is shown by the rise in temperature. So the heat supply, the heat that goes into the metal, the specific capacity. So we define it, specific capacity of a substance is defined as the quantity of heat required to raise the temperature of unit mass of the substance by 1 degree. Memory work only. Okay.
1 minute.
It's on your textbook. I think we are on page 238.
Yeah, this one 4451 lunch.
It's in your book 238. It's all there.
Okay. Wait, answer. I'm seeing in my book now.
Right? 238. So the quantity of heat required to raise the temperature of a mass m kilogram by delta theta in Kelvin is just mc delta theta, or we can call it mc into final temperature minus initial temperature. Right? Theta R is the initial temperature, theta F is the final temperature, delta theta is the change in temperature. Unit is joule per kilogram per Kelvin, or joule per kilogram per degree Celsius. Same. The unit is the same.
Teacher, can you repeat back again 20 seconds ago one? Because my mother suddenly called and it got unmute already.
Quantity of heat required to raise the temperature of mass of m kilogram by by delta theta in Kelvin is just Q is mc delta theta.
MC theta.
So we can also write as mc into theta F minus theta I close bracket, where the theta I is the initial temperature. Usually this is the room temperature. Then theta F is the final temperature, and delta theta is the change in temperature.
Okay.
Unit is joule per kilogram per Kelvin.
Yeah, understood, sir.
Right? Usually we call the initial temperature the ambient temperature or surrounding temperature. I mean the room temperature lah, usually. Unit,
Sir, go back again.
page 238.
Okay, sir. Okay.
Unit, we just write the formula down. No? Q equals to M divided by theta. Q is joule, M is kilogram, theta is
Okay.
Kelvin or degree Celsius. Then our Q equals to C, heat capacity times delta theta. And then Q is also equals to MC delta theta. Remember the small c is the specific heat capacity. Capital C is the heat capacity. So we can see the relationship there. Capital C equals to MC. This is 4 in your book. Okay.
Sir, which page, sir?
Page 238.
C equals to MC. C.
Number 4.
Oh, okay, okay. Oh, so if it's relationship between heat capacity and specific heat capacity, that's the equation lah. Sir.
That's the equation.
Okay.
Okay, so the specific of some value is given. We can see a large value of heat capacity means a rise in temperature of 1 Kelvin, you need a lot of heat. So it means that we compare copper and water. Water got a very high capacity. It means to raise its temperature by just 1 degree, you need a lot of heat compared to copper. Okay with that?
So basically, the water only needs a lot of heat lah.
Yeah, to raise its temperature by 1 degree, that means it is a good coolant. It can take a lot of heat before the temperature rise by 1 degree.
Isn't it copper the right one? Because
Copper
less what
one,
can absorb faster, what?
it can absorb faster, the temperature will rise faster also.
Oh yeah, and it can lose faster also, right?
It heats up faster also.
Oh, yeah. Even though
Okay,
water
now?
in time, but then it will lose over, right?
Hmm.
Okay.
Okay, molar heat capacity. There's your 5 there in your same 5. When working with gases, it's more convenient to use number of mole rather than the mass in kilogram. So we define molar capacity, capital CM, is the quantity of heat required to raise the temperature of 1 mole of gas by 1 degree. So for n mole, and the temperature rise of delta theta is n cm delta theta. Right? The key important, remember, this is your Celsius degree, 0 rise change in temperature, that's 100 degrees. Right? So to convert to Kelvin, we just add 273. This one add to 273. So the key
So
to
example, if the delta t delta theta means it will be 30 means, so 273 plus 30, 303, right?
Yeah. So the unit for cm, molar heat capacity is joule per mole per Kelvin. And to remember, delta theta equals to delta T. Yeah, as shown in the diagram there. Right? A rise at
I
10
can equate it.
Celsius is also the rise at 10 Kelvin. Same thing. Okay?
Okay. 1 minute. Why is it more easier to use mole rather than kilogram? Isn't kilogram more easier?
Usually it's harder to measure, measure the mass.
Oh yeah, depending on a lot,
Just
right?
like your chemistry, you prefer to use mole rather than use kilogram. It's
Mole, mole.
measure the number of mole rather than number of kilogram.
Mm.
Okay, with that?
Yeah, okay.
Anything still not clear?
Molar heat capacity, the formula is theta Q equals
Q,
to NCM delta theta, right?
or delta T lah, same thing.
Same thing, okay.
Yeah, it's number 5 in your book also. It's just they put delta
Yeah, but
theta. You can put
okay,
delta
I
T if you
didn't.
want to.
Yeah, next one can lah.
Molar heat capacity at constant temperature and pressure. Gas can be heated at constant volume. That means you don't want the volume to change. Or it can be heated at constant pressure. So there are 2 heat capacity for gas. Molar heat capacity at constant volume is the quantity of heat required to raise the temperature of 1 mole of gas at constant volume by 1 degree. Right? Number 8 in your note there. Molar heat capacity at constant pressure is the quantity of heat required to raise the temperature of 1 mole of gas at constant pressure by 1 degree. That's the number 9.
So
Same
8 and 9 same definition, except you just took out with volume and pressure lah. Okay.
Same formula as we given you previously. So you can try this question.
Okay.
Molar heat capacity of water is 4.18 joule per gram per degree Celsius. Calculate the molar heat capacity of water. Can?
But what's the mass of water, answer?
1 mole of water has a mass of 18 grams.
That one they won't give in exam, right?
Usually they should give you lah.
Okay. 75.24.
Okay, 75.2 joule per mole per
What
Kelvin.
I did was I did 18 times 4.18. Correct,
Yeah, same thing. I just do it differently, that's all.
That
Same
means
thing.
Q equals to C theta.
Yeah,
Yeah, okay.
as long as you know how to get the answer. So you want to stop now
Yeah,
or you want to
Q
carry on?
equals to C theta. Another day on lah, cher.
Another day.
Yeah.
You want to stop now?
Yes, cher.
Okay, you carry on tomorrow then.
Tomorrow, either Wednesday lah, cher.
Okay, you confirm with me what you want.
Okay, cher. Okay.
Okay, we stop here.
Okay, thank you, cher. Thank you, cher.
Okay,
Bye.
bye bye.